Welcome to Week 8, the last week of hazardous waste treatment and disposal. This week we will evaluate various hazardous waste management approaches, including designs for waste treatment. Regardless of the complexity of the waste to be treated, a conceptual understanding of how chemicals behave is fundamental to designing systems for their treatment. Therefore, engineered systems for hazardous waste remediation and treatment may be considered adaptations of natural processes in which a pathway is optimized to remove the contaminants from soil, water, air, or sludge. This week, two physical phase change processes will be applied to the design of granular activated carbon contactors and air stripping towers. The two phase change processes are sorption and volatilization. In addition, an abiotic transformation process and a biotic process will be applied to the treatment of contaminated soils. Hazardous chemicals that have a tendency to partition onto soils may also be effectively removed from aqueous solutions, such as groundwater or dilute recreational wastes, by sorption and ion exchange processes. One of the most common engineered sorption systems for the treatment of organic contaminants is granular activated carbon. GAC is a high surface area sorbent commonly prepared from natural carbonaceous materials. GAC treatment is usually conducted in cylindrical contactors. The contaminated water is delivered to the top of the contactor, where it is distributed over the top of a carbon bed. A low concentration of contaminant often passes through the contactor due to partitioning and diffusion limitations. So in order to meet typically low cleanup requirements, contactors are often configured in series. The use of 3 contactors in series often provides a low effluent contaminant concentration throughout the service life of the carbon, while also maintaining long contactor runs before regeneration is needed. Volatile contaminants can be effectively removed from groundwater, landfill leachate, and dilute aqueous recreational waste using air stripping. Air stripping is usually carried out in towers in which the water is pumped to the top of a system where it is distributed over slats, rings, or corrugated surfaces. Air is blown countercurrent to the water. The internal components of an air stripper are selected to ensure that mass transfer takes place under effective and economical conditions. The packed material is one of the most important factors in stripper design. The packing material provides surface area for the air and water to interact and creates turbulence in the water stream to expose waste surfaces to the air. You might have figured out that the air stripper transfers the contaminant from air to the water. The contaminant in the water can then be treated in a more efficient and economical manner than trying to treat the airborne contaminant. For example, ammonia vapors in air can be air stripped to an ammonia water solution that can be elementally neutralized with acid to a non-hazardous pH. If an air stripper for acid is also present, the wastewaters from the 2 air strippers could potentially neutralize each other to form a non-hazardous wastewater. Advanced oxidation processes have been used in hazardous waste management primarily for the treatment of contaminated groundwater by pump and treat technologies. Recently, the use of some advanced oxidation processes has been extended to treating contaminated soils and groundwater through the in situ injection of oxidizing reagents. A process that has been investigated because of its potential for transport of the oxidizing reagents through soil and groundwater is Fenton's reagent. Fenton's reagent decomposes hydrogen peroxide with transition elements to generate hydroxyl radicals, which react rapidly with many organic contaminants. Many organic compounds can be degraded very efficiently using Fenton's reagent. One of the advantages of using Fenton's reactions for the treatment of contaminated soils is the potential for the in situ remediation of contamination through the injection or perfusion of hydrogen peroxide. Alternatively, the process can be conducted in batch reactors, which is a more conservative approach. An effective approach to the treatment of surface soils contaminated with chemicals susceptible to biodegradation is excavation followed by biological treatment in slurry reactors. The process provides an inexpensive means of treating soils contaminated with compounds that are rapidly metabolized by microbial communities. Slurry treatments are conducted in existing lagoons or in bioreactors designed and constructed for a specific solid hazardous waste that requires treatment. In considering the process dynamics, the primary limitations in slurry phase treatment are desorption and biodegradation kinetics. Contaminant sorption is a primary consideration in the process design of bioslurry reactors. Because most biodegradable material occurs in the aqueous phase, the desorption rate often controls the bioavailability of the contaminants.